I was just in case there it's a little, you don't need it there.
No, but put it in there, just in case.
Yeah, sorry. So
Hmm?
it's magnetic, so just.
Oh, it's magnetic, okay. Got it. The meeting is being recorded, but I've got it, okay? Okay, everyone can see?
Yeah.
Okay, good. So today it's a black background and white writing. Okay, first and foremost, 1C, exam 1C, sit down, has all the problems worked out, A's, B's, and C's. Therefore, I suggest starting on it right away so that you can do all of them. Okay? On the previous one, I haven't looked at it as what people have submitted. It's one of the problems that, okay, I will discuss the problems in a moment. One of the problems is that people don't start early enough. People do not read the notes. So the mode in which people are operating is that whatever I say over here acts as a substitute for reading the notes. This does not work. This does not work, and what you need to understand is that when I lectured in class, they didn't have notes. They had to take their own notes. So this forces people to engage in the learning of the material, which is not happening. So you can't reduce the amount of time that you spend on the material and expect to absorb it. Let me get my water. I have barricades of wires on every side and should be very careful. So, okay. I also went over all the possibilities very carefully. And so, phone out. Okay, okay, that's okay. You can't see with him?
It's somewhat hard.
Okay. Yes. Now, why don't you bring another table next to him? And then it will be easier. It will be larger. Or just sit it, yeah. Okay, so what I wanted to say is the following, that I looked at the general way in which students have interacted with me. In the case of Quinn, Peter, etc., I taught them everything from Calculus 1 all the way to 270. So, and they all had 163 with me before they took calculus, or at the same time at which they took calculus. The result was that they were completely familiar with the manner in which one draws conclusions. Okay. Now, I looked at all this, the student distribution in this class. Most people took 163 with me. So the logical part of the matter is fine. So in 263, they did not have any problems at all. Most of the people took 270 with me, which means they had the 270 under control. With the result that the first part of 271 and 272 went smoothly. Because that required only knowledge of 270 or 270, essentially. The moment we used stuff that I have not taught you, in other words, basic algebra and trigonometry, everything collapsed. Plus, there was no solved exam for 1C and 2a. Okay, so this is my reading of the matter. So I will extend the diagnosis in the following manner. Insufficient mastery of basic algebra in mastery of techniques, plus lack of conceptual understanding of what it means to solve systems of equation. These two are primary problems. Insufficient understanding of techniques of trigonometry, complete lack of understanding of hyperbolic functions, and since one does not understand what it means to solve equations, in particular, the use of the fifth rule in equational logic, equals substituted into equals yield equals. That means you recognize two things to be similar and you reduce what seems to be unfamiliar to a familiar setting. An example of this occurred when we had quadratic equations, three cylinders intersecting. But I said that by the substitution, u is equal to x squared, etc., this can be made linear. Then you solve the linear equations, then you take square roots. So this is essentially an aspect of looking at something and understanding its deeper symmetries. This is where there are lacks. Is this clear to everyone? So whatever you learned from me, you can apply. Whatever I did not teach you and did not talk about, you have holes in which you need to fill in. Okay? Plus, you have to spend enough time on this. If you don't spend enough time, you will not be able to learn. Okay? Everyone is doing fine on 272. Because in 272, there is only one thing to know. You are solving a linear equation in a function space. In the function space, the dimension of the function space is infinite, but the kernel of the linear operator is finite dimension. I have already told you what the kernel is. So all you need to do is for each problem to apply the algorithm to find the push vector. And that you can do fine, except that either people don't have the time or they're not adventurous enough to try the C problems. Okay. In this term, normally in the spring, performance sort of declines after spring break. I do not know what the reason is, but it must be the same reason that makes rabbits go mad. Because which one has the idiom mad hatter? Mad as a hatter. The hatter is the character in Alice in Wonderland.
They went mad.
I beg your pardon?
We found out the hatters went mad.
Because?
Mercury. They used mercury in the dyeing process
Hmm.
and in construction of hats.
Yeah.
So Mad Hatters.
Ah, yes, okay, yeah. Now, okay, so there is only one thing that I need to teach you conceptually at this stage. Line integrals you have seen, which will come up in 2C. Double integrals and triple integrals you have also seen. What you haven't seen are surface integrals. So, surface integrals, this is not bad actually. What type of computer is this?
That is a surface.
What kind of?
Surface.
It's called a Surface Book, in which.
That's the
No,
number.
but which company? Microsoft Surface Book, okay. Surface integrals and also Stokes theorem. No, I said too soon. I spoke too soon. but we'll see. Okay, first I will describe Stokes' theorem. Stokes' theorem says something rather remarkable. If you have any closed curve, such as this oval, and if you consider any surface of which is the boundary, so you can have a flat surface, certainly. What am I doing? That is not.
You push down hard.
Oh, I have to push quite hard. Okay. This is a surface for which the ellipse is a boundary. Okay. But I could also have something like this. This is like a cap. Okay. Or I could have something like this. You understand? So there's something like this. So it's filled up. So this is the boundary, but the surface is peculiar. So there's a relation between an integral over something over the boundary and the integral over the surface of something, of something, but here we have some sort of a differential of it. So if you integrate some field over the surface, it is related to integral of something else related to the field over the boundary. Okay? So this is an important thing. So this is Stokes' theorem in general. But of course, in 3 dimensions, the boundary is of two dimensions. So dimension of some object, let's say, whatever happened. Why did all move to the right? Pushing and pulling is not achieving what I thought.
It's strange here.
You have to be gentle.
Press detach, so that's confusing.
I pressed attach by mistake.
Yeah, there you press detach. It's
Oh, detach.
Yeah.
Okay.
So there's a function to pull it across, but it doesn't need to do that.
Okay.
If you need to move the screen, it's not 2 fingers, it's just 1 finger.
Okay. Okay. So now, what kind of things can we integrate over a surface? Okay. So let's say the tabletop is what we are considering. But the tabletop is not made of a uniform material. It is made of some material which has non-uniform density. So at every point, density has a certain value, which changes from point to point. Okay, so I have the tabletop can be thought of as a thin layer, and the density of the material is such that if you integrate over the density, you would get the mass of the table. So the density in this case is not mass per unit volume, it is mass per unit surface area. So surface density is what is involved. Okay, so this means in 2 dimensions, for instance, I would have a function rho that sends a coordinate xy to rho of xy from R2 to, sorry, this has to be written. This is a field. I'm thinking of this as a field. So xy, comma, row of xy from R2 no, I think iPad wins the competition. No, I dare not press any harder. What did I do? Did I press the thing by mistake?
So we're just trying to draw a line.
Yeah.
That was weird. Then I tried to do an angle there.
No, but why is it, did it suddenly become less sensitive? So R2, 2.
No, it's actually just for some odd reason, it doesn't, it might be, oh, that was weird.
R cross. But how is it going to be transmitted?
You know, we can just put one of the computers up and point the camera that way.
We can just pay close attention.
Oh, it's not doing what you want it to do.
This happened with the other thing also.
What comes after this?
No, R cross R.
R cross, oh, cross R.
Yes.
Oh, I thought you were trying to draw on there.
No. Cross.
There's a direction it doesn't like writing for some weird reason.
Okay.
Is the pen like connected to the computer in any way?
Yes.
Or is it just a connection?
It's connected in what way?
Bluetooth.
Yeah.
It will. No, we'll take a screenshot. I think we'll press double press or something, triple press or something. I don't use it.
Okay. Let's see if it works. Okay, so row. So if I integrate this, dx dy I should have written before. Dx dy row of xy, that gives you the mass. Rho is here, the surface density. Okay. Now, there is something else that one can integrate along surfaces, and that is a vector field. Okay, so surface in this case, we are thinking of it as a two-dimensional object. So a vector field, for instance, beta is, and the surface could be in 3 dimensions. If it is in 2 dimensions, it is xy going to beta 1 of xy, beta 2 of xy, which is just called beta of xy, from R2 to R2 cross R2. This one is R2 to R2 cross R. Okay. So this gives you a vector at every point, and then you have to do something with it. So you can integrate a vector field over a surface. But this one will not quite do, so we have to think of the surface in 3 dimensions. So the surface is specified by a parameterization from some set into R3. Some set, this set is in R2. Okay? and field specified in R free. Now I have a question. If I were to look at something over here, will that mess this up?
We can go look something up on there.
Yeah,
No, that they don't interact.
they don't interact. So let me change the view. Exit full screen. Documents. I don't want to use notation that does not correspond to what I have in the notes. Handouts. 272 for exam 1C. 272 exam, not 1C, 2C. Okay. So there are, oh, not 8, this is wrong. I mean 271.
Yeah, I almost uploaded my 271 exam.
That's a very dangerous thing to do. Line integral, surface integrals, and Stokes theorem. Okay. Can everyone see? Can everyone see what? Can everyone see me? You see this laptop, right? Not what is on mine.
No.
Okay, that's fine. So, no, I don't want to screen share this one. Although, is it possible to screen share this one?
Yes. We were just screen sharing that one.
Try that and see what happens. Surface integrals, okay. Ah, yes, that would have helped. You can do one thing. We will wait for 5 minutes. Can you go upstairs and print?
It's no longer upstairs.
Where is it?
It's now just the library.
Ah,
So they were removing the computer.
yes.
And I think like separate, like there's a scholar section,
Mhm.
but it doesn't, it's not there.
Ah, but can you print? How long will it take?
I go, what's that? Once for this. Well, I'll take 10 minutes.
10 minutes? So we can talk for 10 minutes while you have to print out this one. Come here, I will show you. Who are there? I can't see anyone.
All right, I see with line integrals, surface integrals, circles there.
Yes. Yeah.
You need another one or is that?
No, that's that one. Who are there in the meeting?
Joe Foster and that's it.
Yeah, and I'm not surprised because no, once it is, what do you need?
Why don't we just pull it? Do we need to get that for him or do we need to show it?
No, that it would be good to have it. Then But can we actually look at this also?
Yeah, you just look at that right now.
Let's see, okay, let's see.
Because my other question is.
Yeah,
Pretty sure. There we go.
This
Actually,
lecture is not going for it.
not exam 1C.
No, this is, okay, I
No, no, that's okay. You go and try to print. I will look at this and we will say what I want to say. Because this is very tricky and therefore I don't want to use notation now that will not correspond.
So I have it here, and I'm sharing on everyone's screen.
Everyone seeing this?
Yeah.
No.
Oh, you're right, I'm doing that wrong.
I see a gray screen. Because Zoom blocks out anything that's.
Yeah, so just stop it. Why don't you go and print it?
Okay.
Print it, but no, but go back to the previous situation. Go back to the previous situation so that I can write.
Why is that not? Oh, is this?
This is the one. Right.
Can I not just do I can do the screen? Sure.
No, we don't want this, we don't want this. Let's go back to the previous situation. Yes.
Okay,
Yeah.
So do we want to pull it up or do we just want that? We'll pull up the notes.
No.
All right, go print it out.
Yeah. Pulling up the notes is not going to help, but I have to, okay.
I'll get 2 copies of you looking.
I can print them out at all.
If you want to copy them.
No, I don't need a copy. Okay. Well, you should have remembered. Because you are the. Okay, so.
I spent my entire day writing 5 line reports.
Okay, let's see. So now coming back. So how is the surface going to do? So these are the specifications which I don't want to change because changing them will mess things up. Now suddenly it doesn't work anymore. Sigma is defined to be there are 2 parameters, S and T, going to, this is on page 12 of the notes. Sigma is ST going to, I don't want to use different letters. C of XST, eta of ST, and zeta of ST from S to R3. So this is the specification of the part of the surface over which you integrate. Okay. No, this is the parameterization of the surface. So the surface has to be specified in this manner.
But isn't the surface?
Yes, but it is in 3-dimensional space. So there are 2 parameters. The number of parameters determines the dimension of the surface. The parameters are S and T, but the surface is embedded in 3 space, so that it must have 3 components. So this is the X component, Y component, and Z component. So in other words, this is simply saying that X is equal to C of ST, Y is equal to eta of ST, and Z is equal to zeta of ST. Okay? Now comes the question of a normal. The surface has a tangent plane at any point, and there's a normal. The normal is the perpendicular to the surface at that point. How do I find the normal? From the parameterization. So there's a formula. The formula is N, which is defined to be equal to 1 over del del S of sigma cross del T of sigma. And this is del S of sigma cross del T of sigma. So you take the cross product of the derivatives and divide it by the norm. So this gives you the unit norm. So these are specifications that you need to understand. So what are we doing over here? We have to specify a surface and we have to specify, we have to calculate the unit norm to the surface. Okay. And so let's calculate a unit normal right away, just to make sure that we understand. So let's take, this is x-axis, y-axis, z-axis, and I'm talking about this surface, which is defined by the equation. So the surface is defined by set of x, y, z in R3 such that x is bigger than or equal to 0 and y is bigger than or equal to 0 and z is bigger than or equal to 0 and x plus y plus z less than or equal to 1. This plane has the equation x plus y plus z is equal to 1. And so the xy plane is z is equal to 0, the xz plane is y is equal to 0, and the yz plane is x is equal to 0. Joe, can you see and hear everything?
Yep.
Okay. Yeah? Okay, so to parameterize oh, just a moment. I have, sorry, this is not what I, how does one, yeah. This is the whole solid. I don't want the whole solid. I want just that surface. So I have to change this. X bigger than or equal to y and equal to. That's just the triangle, this part. Okay, to parameterize S, we need to solve x plus y plus z is equal to 1. You already know how to do this because you've done hundreds of these row reductions. So the easiest thing to do is to say x is equal to, there will be one equation in 3 dimensions, that means 3 minus 1, 2 parameters. There's no difference between the x, y, and z because they are symmetrically situated. So we take the first parameter to be x, and we define the second parameter to be t, and z in that case is equal to 1 minus x minus y, which is equal to 1 minus s minus t. For an exam, the parameterization will require row reduction or some such suitable thing. Okay, so that means now I have a parameterization. Note that this does not tell you the values that S and T should have, right? Because how do I choose the source of the parameterization? Source, yes. That means the parameterization is from some subset of R2 into. So what does the parameterization do? This is a 3-dimensional screen. It takes something in R2 and maps it onto there. That's what the parameterization is doing. So the parameterization sigma is very good. Parameterization sigma sends ST to S T 1 minus S minus T from somewhere to R free. So in order to compare with the notation over there in the notes, you note that C of ST is equal to S, eta of ST is equal to T, and zeta of ST is equal to 1 minus S minus T. Clear? Okay, so now we can compute the normal, but we don't know what this is. So what is being mapped into that triangle? That we need to understand. Do you understand this?
Yeah.
Yeah, so this is, since X is one of the parameters, X is going along the X-axis. So the easiest thing to think of this is as follows. The base of the pyramid is being mapped into the top. So Z is essentially 1 minus X minus 1. Right? That is what is happening. I take any point. So what is being mapped into that surface is just the base triangle. Okay? So somehow I have to specify the base triangle. How do I specify the base triangle? Well, the base triangle, if I call it T, then T is equal to ST in R2 such that everything that lies inside that triangle. So S, what is the equation of this line? The equation of that line is the intersection of X plus Y plus Z is equal to 1 and the XY plane. What is the XY plane? What is the equation of the XY plane? Z is equal to 0. Yeah, so that means the equation of this line is X plus Y is equal to 1 and Z is equal to 0. Because if I plug in Z is equal to 0, okay, I get X plus Y is equal to 1. So in the plane, you have to have S plus T is equal to 1. Okay, that's the relationship between, so the projection has given me this. This is the S-axis, this is the T-axis, this is S plus T is equal to 1. So this T will be T less than equal to 1 minus S. Sorry. S plus T less than equal to 1. And S less than equal to 1. And we still have to say that S is bigger than equal to 0 and T is bigger than equal to 0.
T would also have to be less than or equal to 1.
No, if I say S plus T is less than equal to 1 and S is less than equal to 1, then T automatically is less than equal to 1. Okay? So T actually, therefore, can also be written as T is equal to ST in R2 such that S bigger than equal to 0, bigger than equal to 0, and S T less than 1 minus S and S less than 1. This means I am taking this base triangle, calling the coordinates S and T, and I'm mapping this into this triangle by simply taking the base and pushing it up. At the point XY, it is being pushed up by the height 1 minus x minus y. Do you understand this viscerally?
It gets pushed up by the height 1 minus one.
Yes?
That's what Z is equal to.
Yeah, so look at this. I am constructing a tent. This is the point XY, right? What is the height? Z, but I know X and Y. What is the height that I will erect over there? Suppose this is the pole. This height has to be 1 minus. If I do that at every point, I will get this roof.
Why do we need it? It's already down there.
What do you mean?
So
I am trying to produce a parametrization of the surface. The primordial idea of a surface is that it is some subset of the plane. So in order to produce the surface, I have to map every point of the subset of the plane in space. That is exactly what I'm doing.
So we have the one that there, every point that they just give out, give us.
I don't know.
This is a geometric interpretation of the parametrization.
So
What does the parametrization do? It takes a point ST in a subset of the plane, and it maps the point ST into C of ST, eta of ST, zeta of ST. So,
wait, so the height at each point.
of course,
Okay, yeah. It basically shows what
the mapping is doing.
the standard side is.
Yes.
Okay.
What the height of the slanted side is?
Yeah.
Okay, tell me what the point. Let's take an internal point. The point 1/3, 1/3. That is internal. What is the height at that point?
1 minus 1/3.
Which is? Is
1/3.
yes. So the point 1/3, 1/3 goes to the point 1/3. Okay. You see, this is what is lacking. When you look at the parametrization written algebraically, it should immediately tell you, give you this picture. When you read the notes, this is what must happen. But I don't think this is what happens. Yeah, if it doesn't happen, it means that you see a long set of squiggles all over the board, but it doesn't give you a picture. I can't create the picture in your heads, and you cannot gain the ability to create the picture unless you actually sit and work at this. This is what you're not understanding. It will not automatically happen. Okay, so you have to devote more time to it. So when I am doing this, the picture comes automatically. Sometimes I have to think carefully about what the picture is, particularly in high dimensions. But it is only because I spent the time on these things sufficiently so that it happens automatically now. If Rivi were here, I would use music as an example also. To someone who is not musically trained, looking at a score does not give you an idea of the tune. In order to get an idea of the tune or even to be able to hear it within your head, you have to spend time translating from the visual mode into the oral mode. Do you understand what I'm saying?
Yeah, I understand.
Yeah. Okay. So now let's calculate the normal. The normal would be, first I have to calculate del S of sigma cross del T of sigma. Oh, this is a bit, this is,
Sorry.
no, it's getting hot
Yes.
to the touch. Okay. So this is del S of ST 1 minus S minus T. Whatever happened here? Cross del T ST 1 minus S minus T. Now, do you understand that this is extremely inefficient? Because our agreement was that before you come to class, you should read the notes. But no one has read the notes. So effectively, what am I doing? I'm reading the notes out. Normally, I don't do that, but today I am doing that because I don't want to use different notation. Because this notation is very tricky. And if I am not consistent, then you will have a lot of trouble. Okay, you agree that I told you all these things before?
Yeah.
Okay. So equals del S of S, del S of T, del S of 1 minus S minus T. Cross del T, just a moment. Del T of S, del T of T, del T of 1 minus S minus T, which is equal to 1, 1, minus 1, cross, oh, sorry, not 1, 1, 1, 0, 0, 1, minus 1. So I have to take the dot product of these three things. So this is equal to E1, E2, E3, or EX, EY determinant. 1, 0, minus 1, 0, 1, minus 1. No, that is wrong. 1 minus S minus T, so that is correct. So this is equal to, let's see, 0, minus 1, 1, minus 1. Minus 1, minus 1, 0, minus 1. It won't shut it off.
No, it's now.
1, 0, 0, 1 is equal to, this is 1 minus 1, that is 1, and this is 1. Does this make sense? Why does it make sense?
The calculations make sense.
No, what does it make? What does make sense mean in this context? Do I have any way of visualizing this so that it corresponds to the picture that I've been using so far?
Well,
Make sense can only be used in this way.
so
Okay,
these are recorded.
no, this is the normal. I calculated n. This is n. This is n. The normal to the slanted side. But in other words, the numbers should tell you what it looks like. If it doesn't, then you're like the nurse who looked at me and said, did I tell you the story of the nurse? No? So I didn't say it in this class.
This is like the going to the store thing that you told us about.
I've never
No, no,
heard
no.
A story.
They-
like this.
The CCP Institute is a wellness program, and they measured various things. And the idea was that if they measured various things and told all the faculty members, then, and the people who work here, some of them would go and exercise, and therefore the health in general will improve, and therefore they will not increase our premiums. So I went there, so they made me stand somewhere where they drop this thing on your head and measure your height. Then they pinched with a pair of slide calipers here and said something about measure the
Like to
thing.
see in your skin.
Yeah. And then the last thing that they did was measure my waist. So then they said, when I went to see the nurse, she smiled and said, you are 6 feet 6 inches tall, weigh 140 pounds, and have a 40-inch waist. So I told her that, are you looking at me or are you dreaming? But it made no difference to her. Then she said, but the computer says so. So I said, what you just described is a long thin pole with a disc attached in the middle. So she smiled even bigger and said that, but the computer says so. So those numbers meant nothing to her. So later on, I thought to myself, how could they measure my height to be 6 feet 6 inches? Then I thought maybe it came out as 66 inches. And then whoever entered the data sat in front of the computer, and 2 windows came up, feet and inches, but division by 12 was not on the syllabus. So 66 inches is 6 feet 6 inches. That is the easiest solution. So it adds a foot to my height. The weight was roughly correct. I thought, how would they measure the waist to be 40 inches? I thought it must be that that tape had only one number on 40. So anything you measure will be 40 inches. I have no other explanations. Okay, the others had worn off or something. So why am I saying this? Because now you are like the nurse. You look at the vector 1, 1, 1, but you have no idea what it means, or if it makes sense. All you can test is whether the calculation was done correctly. That doesn't tell you if it actually is meaningful. Okay, so let me draw
Is
the.
that's the end point.
Hmm?
It's the point side of it.
No. How can the end point of the coordinates of each point, each corner are 0, 1, 0, 0, 1, 0, 0, and this is 0, 0, 1.
Yes.
This is the surface. These are the components of the normal. What is this point? Yes, it is 1/3, 1/3, 1/3. And if you have this is the normal. So this normal is symmetrically situated with respect to the axis and should be central. So if you go from point 0, 0, 0 to the point 1/3, 1/3, 1/3, that vector is 1/3, 1/3, 1/3. So this is in the same direction because it's a multiple. Do you now understand how not to be the nurse? Clear to everyone? Yes, but it has to be for every situation. So you see, I am trying to communicate to you that the reason why this course is difficult is because you need to constantly imagine the things, and nothing that I can do will cause the images to develop in your head. Nothing whatsoever. I can just go very slowly over the stuff. Now, what is the unit normal? So the unit normal I have to divide by the norm. So n hat is equal to 111 divided by 111.111. So that is equal to 111 divided by square root of 1 plus 1 plus 1 is equal to 1 over square root of 3, 111. This calculation will be necessary. Either just the normal or the unit normal, but it doesn't matter. So now, so if I have now beta, which is a vector field, beta sends x, y, z to beta 1, beta 2, beta 2, beta 3, I suppose. Beta 1, x, y, z, beta 2, x, y, z, beta 3, x, y, z is equal to beta of x, y from R3 to R3 cross R3. This is the vector field. So we will take so what is the surface integral? The surface integral of beta over the surface sigma with the normal n and with the parameterization small sigma. Okay? These are the factors, is the double integral ds dt over S is what is being mapped of beta composed with sigma st dot del del s of sigma cross del del t of sigma. That's how the surface integral is defined, and of a vector field. Let me just check the notation for the scalar field. Where's the scalar field? Okay, surface area of sigma. Sigma is defined to be the integral over S ds dt, the norm of del del S of sigma cross del del T of sigma. This is the surface area, and where's the scalar field? Yeah, this integral of the scalar field phi, so I should write phi down. Phi sends x, y, z to phi of x, y, z from where to where? From S to, sorry, from R3. We do not have R3, we have some subset of R3, and R3 cross R. So this is a scalar field, and the integral of the scalar surface integral of P sigma n small sigma is defined to be ds dt phi composed with sigma st times the norm of del s of sigma cross del t of sigma. So there are three kinds of integrals, either the surface area, which is to integrate one, or the integral of a scalar field, or the integral of a vector field. And you need the field, you need a parameterization, and you need a normal. Why do you need the normal? Because I've shown you things like the Möbius band, which does not have a well-defined norm, because it has only one side. The surface has to be a surface with two sides, globally defined. Okay, so far, I have calculated the normal for the slant surface. Suppose I want to find the area of the slant surface. What is the area of the slant surface? I will do it by ordinary geometry first, and then I will do it by integration. Ordinary geometry, what is the formula for the area? Base into height. Okay, so this will be the height because this is symmetrically situated. The midpoint is, this point is 0, 1, 0. This point is 1, 0, 0. This point is 0, 0, 1. Right? Okay. What is this point? What are the coordinates of that point?
One half, 0.
Yes, it's 1/2, 0. Because in order to find the midpoint, you add the coordinates and divide by 2. So that is 0 plus 1/2, etc. Okay? Okay, what is this base? How much is this base? Theorem of Pythagoras that one learns in childhood? No. This is the right triangle. Square root of 1 squared is equal to square root of 2. So the base is square root of 2. What is the height? That is this distance. No. Don't guess. It doesn't make any sense. How do you find it? How do you find the distance between 2 points? The distance between A1, A2, A3, comma, B1, B2, B3, you see, is A1 minus B1 squared plus A2 minus B2 squared plus A3 minus B3 squared. Do you see the weaknesses that you have? These are gaps in the background. I did not teach you analytic geometry.
Is. We look at the one correct?
No.
Because.
Wait, let's actually work it out. Okay. First, let's have the line. No, first of all, this point is 0, 0, 1. So, okay. A1 minus B1 is equal to 0 minus half squared. Plus 0 minus half squared plus 1 minus 0 squared is equal to square root of 1/4 plus 1/4 plus 1 is equal to square root of 3/2. You can't guess these things, you have to calculate. We can see this in a different way. This is an equilateral triangle. This angle is 60 degrees, that is pi/3. So this height will be this side, which is square root of 2. Square root of 2 times this side times. So to get that side, what do I need, the sine or the cosine? The sine, right? So it is square root of 2 times sine of pi over 3. That is square root of 2 times sine of square root of 3 over 2, which is equal to. Here I am teaching you another thing that is important. You always try to calculate something in 2 different ways and see if the answers agree. All my exams are designed in this manner. So far, so good?
Like square root of 3 over square root of 2.
Yes. That's that height. So let's calculate the area of the triangle and then we'll take a break. Area of the triangle, therefore, half base times altitude. Half base times altitude. What is the base? Square root of 2. What's the altitude? Square root of 3 over square root of 2. So what's the area? Square root of 3 over 2. And now we shall see that by integrating, we should get the same area. Okay. Now we have a break. You, What is happening to you?
I think we ate some Indian food 2 days ago,
Mhm.
3 days ago. And that's it. I didn't even realize it was bad food, like I thought I just ate some Indian food and having got problem. And I was like, oh, I'm just it's gonna bother me for a day. And it hasn't stopped in a while. So I'm like, what? Oh, you're 100% cheating. I'll eat it. And she felt sick. I'm like, oh, the food was just bad. So probably never ordered from that side.
You did not heat it up, or what?
I ate half of it, because I got kind of full eating, because I had a number and I remember the little potato, like the potato thing that's. It's like a dumpling with fried potato in it. I can't remember what it's called.
Oh, samosa.
Yeah, samosa. Yeah, I had one of those, like entire number, and so I stopped eating it halfway. And it did not go well for us.
So you had an upset stomach.
Yeah, I mean, it seems to be going away. It's, I've been yesterday, we're going around New York yesterday, because we had to go to the Malaysian consulate to make our marriage official in Malaysia. And we'll travel there. Came back.
Is she Chinese, Malay, or Indian? What origin?
Is half Malay and Chinese. And so the Malaysian consulate, she's just Chinese. Which she actually told me yesterday was like, she was her mom, like her mom would just call her Chinese and they recognize her as Malay, just kind of weird. But she's
Her mother is Chinese.
Her mother is Malay.
Her father is Chinese.
Yes.
Are we being recorded, or?
I don't know if it's separate word.
I was not recording at all. So it depends on, but don't do anything.
It's not okay. It's so those fun little bit true. And I'm still exhausted from it. And I'm getting kind of irritated. It takes me so long to recover from doing it. But it's gotten better, which is not a good thing to say. That like the health, like it used to take 2 or 3 days now, so it's like 1 day out. And I spent like half the day going through 272 and doing some of the work for that. So by the time you came out, I had like 2 or 3 hours focused, 5 hours unfocused, doing stuff, and I'm just like,
Are you recording all still? Okay, okay. Shall we start? Okay, so Joe, are you still there?
Yep, I'm here.
So have you followed so far?
Yeah,
Okay, so now I have to find the surface area by a difficult method, which is by integration. So surface area of sigma is equal to ds dt of the norm so I've already computed the norm. So this is ds dt. What was the norm? 1 over square root of 3, right?
Or you told us the norm was the vector.
Yes. No. Norm was not the vector. Norm is just the length of the vector. Oh, sorry. The norm of the vector turned out to be just square root of 3. Sorry. Yeah. Norm is just square root of 3, which I calculated before. Yeah. Square root of 1 squared plus 1 squared. So that is the norm. Okay. So this is, and this has to be integrated over that little triangle. Okay. So this is equal to square root of 3 over s. ds dt. Now this is very easy. So this is square root of 3. dt has to be integrated from t is equal to 0 to 1 minus s. And then ds goes from 0 to 1. That's over the triangle. I already wrote s. Remember, s was bounded by various things. It was the base triangle. So this is s plus t is equal to 1, which is the same as t is equal to 1 minus s. I'm integrating over t first, which means I'm going in this direction. So t goes from 0 to 1 minus s. And then I will integrate this way, 0 to 1 along s. So this is equal to square root of 3 ds 0 to 1. This is t 1 minus s 0. So this is equal to square root of 3 0 to 1 ds. This is 1 minus s minus 0. This is equal to square root of 3 integral from 0 to 1 ds minus integral from 0 to 1 s ds times s. So this is equal to square root of 3 s between 1 and 0 minus half s squared 1 and 0, which is equal to square root of 3 1 minus 0 minus half 1 squared minus 0 squared is equal to square root of 3 1 minus a half times 1 is equal to square root of 3 1 minus half, which is equal to square root of 3 times half, which is equal to square root of 3 over 2, which is exactly the answer that we got by the ordinary method. So I'm trying to teach you two things. One is that you calculate everything in two different ways so that you know that the answers agree. So the probability of it's being wrong is reduced. Clear to everyone? The other thing, which is far more important and far more difficult, that when you read these, which none of you have done, you need to cultivate the habit of imagining the things in your head. There is nothing whatsoever that I can do to produce the images in someone else's head. I can only act as a stimulus, and I can also give examples that are likely to cause this to happen. but it is not guaranteed to happen. But this, what I'm trying to do is completely against the utilitarian point of view. What is the least amount of work that I have to do to get the grade that I want? These two are contradictory goals. These two, so in other words, since they're contradictory, if one is using one of them, the other doesn't happen. Is this clear to everyone? So what I had initially told you, you see, this is, it's very important for you to understand this, because in 163, when people started, there was horrible COVID. Plus the material was unfamiliar. I was the computer monster, whether explicitly so conceived or not, but I have proof. The proof is the measurement of the size of Riviera's mouth. When he realized that I was the person who had been writing to the class. Okay, so, but then people started working actually. Maybe Juan had something to do with it also, because Juan met with the people before. I realized after talking to Max that it is very important to meet with the people. But then people started working and they got the material. But 163 is simpler than this. Would you agree? 163 is simpler because it doesn't require you to imagine anything. Then once people understood 163, when they went to 263, the language they had already acquired. And 263, whatever they had to imagine, because there was a very easy book and solved exams, they had an easy time. I really saw that it's very rarely that in 263, someone makes mistakes. It doesn't happen for some reason. Okay. Then came 270, which was another shock. But people halfway through mastered row reduction, which is basically the only technique, and they could imagine flat things more or less. No one attempted any of the problems, the 15 problems that are in the problem set, because they met their grades. But those 15 problems are precisely the missing algebra. So I actually did solve some of them in class when I lectured on algebra. Clear? So now we are at this stage. You should have a realistic understanding of where your heads are at the moment and where your learning is. So if you forget the details of what we learned, that is perfectly fine. What you should acquire is the ability to learn the material, fill in, diagnose where you have gaps, fill those in so that you gain a certain mastery. This is the most important thing. I don't know to what extent that I am successful in allowing you to develop this. Okay, now let us do something else. Let us integrate a vector field. And since you have reduced me to reading my own notes, I will look at the vector field that I did integrate. I think I must have. Incidentally, all these notes were written up while I was in quarantine in various cities in India. Where is the, I'm sure I integrated. Yeah. No. Yes, there may be Stokes theorem. This, yes, I found it. But what is the vector field that I have to integrate? Yeah, this is on page 19. Integrate the vector field over the triangle. 19. So beta,
We don't pay them.
hmm?
So, the PDF doesn't have page.
No, it does have page numbers. Yes. How can the printer print without page numbers?
They printed none of the page numbers.
Yes.
Yeah, it's, look, it doesn't, it didn't, it
Cut
cut
it
off,
off.
it for some odd reason did not print the footer. Because it also doesn't have, please, what is this?
So
What is
you-
that? Please check any
Errors.
errors.
Yes,
Yeah, that's at the bottom of every page, right? Yeah, it cut off the footer. I don't know why. So,
I think I have this printed at home.
You also have your iPad at home. But that does not help us. I can't write remotely on your iPad at home. But I am completely persuaded that the iPad is the best thing to get.
yeah, definitely, because that's not supposed to be, that's supposed to be three different things in one, so.
It doesn't matter, but the technology should be such that,
It wasn't that way 6 years ago.
Yeah.
That's a 6-year-old.
but his iPad is very old.
Years ago, I had one. It was 2017. He's saying what? Can you give it that? What year did you buy it?
I didn't buy it, I got it, high school. Yes, and it was, like a Comcast sponsorship for my school. And they give like a really old generation iPad to us.
Anyway, but it works perfectly. Anyway, so let's do this one. So the vector field that I'm supposed to integrate is beta is equal to x, y, z going to y dz is equal to 0, 0, y from R3 to R3 plus R3. I have to tell you, when I wrote those notes, it was in Mumbai.
R3 cross R3 cross R3.
R32, sorry. I still remember. My flight was to go from here all the way to Calcutta. When we landed in Mumbai, they said that the flights to Calcutta had been cancelled. There are people sitting at desks. You go choose a hotel and you have to stay here at your own cost. How long? 15 days. So I went to the hotel. They said that you have to go to that room and you may not come out. And the food will be served to you at these times. They will put it on a tray outside the door, knock and leave. So after they leave, then you open your door, get the food, take it inside, eat. Then you put the tray outside and call downstairs for someone to come and collect the tray. So this happens 3 times a day. And so I amuse myself with writing up the notes. So these notes have a long history.
You're really a prisoner.
I was a prisoner. I was.
Well, at least you got the right notes.
Yes. Then what happened? Oh no, actually I know mathematicians who were imprisoned as what is the word? Someone who goes against the government. No, dissenters. Yeah, a dissenter, yeah. The Russian mathematicians who were put in prison, but they sat there, they were not given any paper. They sort of, in their heads, produced a lot of very good, very important mathematics actually, while in prison. So, yeah, I at least had all my stuff with me.
And it just happened when you're bored.
Hmm?
The things that they can do when they're bored.
It's the only way you can say same.
Yeah. Okay, so now This is the one that I will do. So the parameterization we have already done. Now, in order to integrate, I have to compute. Oh, this one I have also calculated the normal, so that's fine. So surface integral of beta over sigma n using that parameterization. The parameterization I also have is equal to, so before doing this, I have to compute beta composed with sigma. Beta composed with sigma of ST is equal to 0, 0, y with x replaced with s, y replaced with t, and z replaced with 1 minus s minus t. That was the parameterization that we used. So this is equal to 0, 0, t. Okay? So the surface integral of beta sigma and small sigma, this is incidentally on which page? 21. Is equal to integral over s ds dt, beta composed with sigma. I have never in my entire life done this, which is to copy from something that is written. You have reduced me to a machine. Throughout my life, I just came into the class and made up whatever came into my head and lectured. So these came up there in my head when I was in quarantine. So, okay. But given del del S of sigma cross del del T of sigma, which is equal to S ds dt. This one I just calculated to be 0, 0, t. The other one I calculated to be 1, 1, 1. Note that we don't take the unit normal, we take the regular. It could also be the case that
the top cutoff, like it printed per page.
Okay.
There's nothing that.
Okay. Okay.
It's a instinct.
So this is ds dt 0 plus 0 plus t is equal to ds dt times t. So that is equal to, now we know exactly where to integrate, of course. So this is t is equal to 0 to 1 dt. The order of integration over here is different from the one that I used before, but that is fine. So here it is integrating over x first, then over 1. S is equal to 0. S is equal to 1 minus t ds of t. Okay, so here the integration is first over x, then over y. So one is going this way. This is s plus t is equal to 1. That means s is equal to 1 minus t. And then one is projecting onto the y. So this is 0, this is 1. Okay, so this is equal to dt. T is equal to 0 to 1. This is ts. Ts, s is equal to 1 minus t, s is equal to 0. So that is equal to t is equal to 0 to 1. T, 1 minus t minus t times 0 dt. So that is equal to t is equal to 0 to 1, t minus t squared. Anyway, I'm not going to bother doing the calculations which are done over there. So this turns out to be 1 over 6. Page 21, 22 of nodes. Okay? So I have computed a surface integral. The only thing over here that you need to keep, that need to pay attention to is that the normal, since it was a flat surface, the normal is constant. It doesn't depend on x, y, and z. But if we had a curved surface,
This is the surface integral of the base.
no. The surface integral is over the slant thing. Surface integral, we integrated a vector field over the surface. But the surface is flat. Therefore, the normal is the same at every point. Okay? But if you had a curved surface, like the surface of a sphere, or the tricylinder, then at this point the normal is this way, this point the normal is this way, this point the normal is this way. The normal depends on x, y, z, or s and t. Here, this is a simple problem because only the field depends on s and t. The normal does not depend on s and t. There's an example worked out over there where the normal also depends on s and t. Okay, is this clear so far? Okay, so now let me see if I did this.
Surface area. Area of 3 over 2.
True, yes.
Here's 1 over 6.
It's not the surface area. This is the integral of the vector field over the surface. Yeah, that means it's the amount. So suppose the vector field is this. The vector field is 0, 0, y, right? Okay, so we can understand this. At 0, it is 0. Let's take the point half, half. At half, half, it is 0, 0, half. Right? 0, 0, half means it points in which direction? So 0, 0, half. So z is half. So that means the vector field at that point just looks like this. What happens at 1, 1, 1? 1, 1, 1 is this point. So the vector field is 0, 0, 1. So at every point, there's some vector attached. How should you understand the vector? You should understand the vectors as the velocity of, let's say this is underneath inside a river, flowing river. So the velocity, so that the vector is the speed of the water flow at a particular point. So now think of this as sort of a net. So the integral of the field, vector field, measures the flow of water across the net in unit time. That can be used in hydroponics. If you have things growing in flowing water, if you want to maintain a certain concentration of nutrients,
So I don't know.
okay?
Don't think so.
No, you can calculate it in this way. So you have a lake. Yeah. Yeah. Or if you, for instance, if you want to measure blood flow across veins. Yes. So this is the mathematics that is used. So when blood flow is stable, we are fine. There are many diseases in which the blood flow becomes turbulent. Okay?
So.
Yeah, I mean, that's a different thing. So this is just how you measure the flow across a certain surface. Okay, so now Stokes' theorem. Let's see. Green's theorem in the plane and Stokes' theorem. Where's Stokes' theorem? Where is the statement? Stokes' theorem. Okay. Line integral okay. Line integral of beta over the boundary is equal to surface integral of curl of beta over sigma. So if you are given a vector field, if you integrate curl of beta over sigma, then the line integral of the vector field along the boundary should be equal to it. So let's compute curl of beta. Curl of beta is equal to right? For the vector field that we chose, beta was 0, 0, 1. So this is equal to del y minus del c 0 minus del xy minus del z 0 and ez del x0 minus del x0. So this is equal to 1 minus 0 minus 0 minus 0, 0 minus 0. So this is equal to 1, 0, 0. Okay, so surface integral, surface integral of curl of beta over sigma is equal to, there's the formula for the surface integral. This is not calculated over there, I think. Which page was it? 21, 19 to 21.
23.
Surface area, the surface area comes later. Yeah. Okay, so before I can calculate this, what do I need to do? Curl of beta composed with sigma. That is what I need to calculate. So this is equal to curl of beta turned out to be how much? 1, 0, 0. 1, 0, 0 with x, y, z replaced with s, t, 1 minus s minus t. Now, since x, y, and z don't occur here, you have to put parentheses in the substitution things. In the previous situation, I forgot to put the parentheses somewhere further back. I don't want to do that because that may mess me up. So this is 1, 0, 0. This is 0, this is 0. Okay, so now surface integral of curl of beta sigma n sigma is equal to integral of a S ds dt, curl of beta composed with sigma dot ds sigma cross dt sigma. Now it is working quite well. I don't know, maybe I have become better. Oh. So curl of beta in with sigma is 0, 0, 1, right? Isn't that what we calculated just a moment ago? No, 1, 0, 0, sorry. 1, 0, 0. 1, 0, 0 dot 1, 1, 1. Right? So this is equal to S ds dt 1 times 1 plus 0 times 1 plus 0 times 1, which is equal to S ds dt times 1. This is just equal to the surface area, right? So that is just equal to what? What was the surface area? Square root of 3 over 2. Which means now, if I integrate this vector field along the boundaries, I would get precisely the same answer, square root of 3 over 2. Okay, so how do I integrate? So this is, let's call this 1, let's call this 2, let's call this 3. What is 1? It is x plus y plus z is equal to 1, intersect z is equal to 0, which means it's x plus y is equal to 1, z is equal to 0. What is 2? X plus y plus 1 is equal to 0. And x is equal to 0, which is the same as y plus z is equal to 0, x is equal to 0. Can I, okay, what, this is 2. What about 3? 3 is x plus y plus z is equal to 1. Y is equal to 0, so that means x plus z is equal to 1, y is equal to 0. Okay, so 1 can be parameterized as, how can you parameterize 1? Well, 1 is, this is a parameter, one parameter. Okay, so x is equal to t, y is equal to 1 minus t, z is equal to 0. And it goes from the point from 1, 0, 0 to 0, 1, 1. So x is equal to t is equal to 1, y is equal to 1 minus t is equal to 0, z is equal to 0 is equal to 0. That gives me that. How much is t? T must be 1, right? T is equal to 1, 1 minus t is equal to 0, which means 1 minus t is equal to 0. So it means that t is equal to 1. And at the other point, what will happen? 0, 1, 0, sorry. So x is equal to t is equal to 0, y is equal to 1 minus t is equal to 1, and c is equal to 0, which means t is equal to 0. 1 minus t is equal to 0. Which means t is equal to 0. So integral, sorry, line integral of the vector field beta along 1 with this parameterization, which shall be, what shall we give the parameterization pi? Okay, is equal to integral from 1 dt. What was beta composed with? Did I compute? What was beta? 0,0y, right? Okay. What did we, okay. Beta is 0,0y with x replaced with t, y replaced with 1 minus t, z replaced with 0 dot d dt of t 1 minus t 0. So this is equal to t goes from 1 to 0 dt 0,0y. So 0,0,1 minus t dot d dt of 1 is 1, d dt of 1 minus t is minus 1, 0. So this is equal to dt 0 plus 0 plus 0. Ah, very good. So this is 0. I have 2 more sides to do. What time is it now? So then I will not be able to finish the 2 other sides. I am inclined to leave that as a problem, or I can do it next time.
I will.
Okay.
I don't think we're gonna do it like we.
No, that I know. But please try to put it on YouTube tonight. Okay. And at least announce it on this. Well, if you announce it on Discord, you can always send it to me at the same time, right? Okay. So we will stop here. Joe, are you awake, asleep?
Yep.
Okay. So then I will end the lecture here.
Thank you.
Where do I stop? Today is, where's the meeting? I don't understand how to stop it. It usually shows me